Apologies if I've been sleeping through all your amazing talks because I came straight from the Johns Hopkins Applied Physics Lab where I gave a similar talk yesterday morning at 10 a.m., jumped on a plane and haven't had any chance to sleep. Uh, but but yeah, I'm here to talk to, well, honestly, I can't follow up that great talk. I love the actual detail on the attitude control. I'm instead going to talk about, well, me. There's going to be a few interesting stories here, but for those of you who don't know, I'm Scott Manley. I'm sort of on the internet. I love talking about space and space flight. I love to know what I'm talking about. I've learned a lot of really interesting things and I've told a lot of cool stories. Here's some of my most popular videos, actually. These are my most popular videos, and you see that, well, we've got Chernobyl and we've got the Titan submersible. People love to hear me talk about disasters. But, you know, we have things like orbital mechanics around the moon. We have like a relativistic ray tracing thing where I showed what happened when you get close to a black hole. And of course, you know, SpaceX's first Starship launch where they managed to dig a giant hole in record time. Anyway, I've made like thousands of videos, millions of subscribers, and I kind of want to talk about how I got started. And for me, I was born in 1972, grew up, and then 1977 I saw Star Wars. Hugely formative influence on who I am, and it still sort of informs my attitudes today. I instantly wanted to be a spaceship pilot, right? This is from Halloween a couple of years ago. I did all that sewing myself, by the way, which is a real engineering skill. And just coincidentally, interesting fact about me, a few years ago, I moved to a little town called San Anselmo. And it turns out that this is the best place to be a spaceship pilot because it's also where George Lucas lives. And so in the town square, you know how town squares have like statues of famous people? We have statues of Yoda and Indiana Jones. But yeah, obviously in the 1980s in Scotland, I wasn't going to be flying real spaceships, but I did fly a lot of video game spaceships. This is pretty much my first computer, right? ZX Spectrum, Sinclair, you know, 48K of memory, played a lot of Elite. But yeah, never flew a real spaceship. Yeah, I do now fly planes, however. That is a fantastic thing. Here's some amazing pictures of things that I have done. That obviously we've got a biplane there, pit special inverted, and that's the plane that I own in the middle. And this one on the right, I'm not flying those planes, I'm backseat, but the one second from the right, I'm in the back there. And the one second from the left is being flown by the current NASA administrator, Jared Isaacman. I got to fly with him in Montana, and we had a lot of conversations about what NASA needed to be doing. So it's a really interesting time to be giving this talk, given what's been happening in the last 24 hours. So obviously, right, coming back to me growing up in the 1980s, playing video games, I realized that, no, I can't be a spaceship pilot. And also, being in Scotland, I probably can't actually be an astronaut, which is actually a real job. So I sort of settled on becoming an astrophysicist, and I came to this place you might recognize. And in the rest of the world, they're all like, oh, that looks like a cool old building. And you guys are saying, wait a second, the physics department is off the right there. You didn't even get it in the frame, right? I spent 5 years here, did bachelor's, and then I did a master's in something called computational physics, basically studying how to not destroy your code using floating point numbers. I desperately wanted to stay in academia. I got a position at the Armagh Observatory studying postgraduate work on asteroids, comets, and things like that. I actually wrote a bunch of code. When you're doing astronomy research in Ireland, you tend to be a theoretician because it's cloudy all the time. But those computer skills were very useful to me. And I was able to sort of step sideways from astronomy as I realized I was never going to complete my PhD. I got recruited by a company in the Bay Area and yeah, I became a tech guy. I worked in a bunch of different companies. I was the last engineer ever hired at some company called Napster. I was actually working on how to hack security systems, also the security here with Qualys. And I spent 15 years at Apple. which I just left that position last year. So now I am a full-time content creator, which means I get to be a globetrotter and give talks at conferences 24 hours apart with no sleep. So yeah, that was a big change in my life. I would go out to parties, I DJ'd, I met my wife, had a family. This is me practicing with my, well, I think she was like a 9-month-old at that point. And I still DJ today. This is me performing at the Astro Awards in Austin a couple of months ago. Like we get into it in America, right? Like these guys, they're all like guidance engineers. They're building rocket engines and they are, well, eat, sleep, space, repeat, right? This is what I'm doing right now. So anyway, how did that turn into something on YouTube? So what got me to get an account on YouTube was that I bought an iPhone, or my wife bought an iPhone, and it was a 3GS. It was the first one that supported videos. And that meant you could take a video and instantly post it to YouTube. And of course, being a dad, I posted a whole bunch of garbage about my kids, right? There's my daughter wearing a cute costume, throwing a basketball, being in a box with a doggy, and oh yeah, right down the bottom, that's her playing a video game called EVE Online, which is sort of notorious. It's an MMO which is brutal. There's no like refunds or whatever. It has a fully featured economy, a universe with thousands and thousands of players, and infamous moments where great wars happen and people lose thousands and thousands of dollars, hundreds of thousands of dollars of assets. I posted her playing that because people said it was a very difficult game and I wanted to make a joke on the internet. But jokes on the internet sort of acquire views. I had the nucleus of an audience. By the way, the kids did actually work out. They didn't get permanently scarred by being forced to play video games as a child. This is them at the DART launch in 2022. But yeah, having a nucleus of an audience, I created a video which was my first pure science video, and it was based on my research in Ireland, and it was essentially the discovery of asteroids over like 30 years. And so what we're seeing here is a map of the solar system, right? And you can see the planets, you can see the sun, and you can also see these white dots that are appearing. And that is where these asteroids were when they were discovered. So in the bottom left, you'll see this is like 1983. We know 11,000 objects. And as time goes forward, we're discovering more and more. Now, in the 1980s, you're doing this discovery with photographic film. You're basically having to take a photo, get it developed, send it off with some student to actually look at the images, find the moving objects, catalog them, do astrometry, and then maybe a few days later, you go back and you find that dot has moved. And then you start to do work a little more and you figure out there's an object there. So what you're also seeing here is a pattern, right? The place that we are seeing asteroids is opposite the planet Earth because, of course, you're looking away from the sun. There's other patterns that start to emerge. You'll start to see like flashes where there was a survey in a particular direction like that. It was lined up with the planet Jupiter because they were looking for new moons around Jupiter. People that know how to look for moons also know how to look for asteroids. So now we get into the sort of mid-1990s. Electronic imaging really starts to take off, and that accelerates the discovery because you go from taking days to develop your film and analyze it to getting it out right away, putting it into a computer, finding those dots, being able to figure out where things are changing and instantly make follow-ups. So the discovery rate now is really starting to shoot up. I originally did this, the original code was like for 50,000 asteroids, and yeah, it very quickly shot through that after I wrote it. You can also see another interesting pattern here. So first of all, the sort of discovery rate appears to pulse, like twice a second. And the reason for that is the best time to look for asteroids is when the skies are dark. So new moon. When there's a full moon, the discovery rate is much lower. Another thing you'll notice is sort of down the bottom here, there's usually a gap. And that's the reason for that is because most of the places that were doing this, or many of the places, were in Arizona. And that's around the summer monsoon season, so everybody was clouded out at that point. And you'll also see, by the way, we've now shown all the green objects are in the main belt, the yellow ones are Earth approachers, and the red ones actually cross Earth's orbit. And so towards the end, about 2009, 2010, there was a final interesting one showing the WISE, the Wide Field Infrared Survey Explorer, which looks forwards and backwards along the orbit. That discovered a huge numbers of objects, and this continues to this day. We've got millions of objects out there. So anyway, yeah, that was my first big hit, and I had a core of a science audience who started to follow me, and I could talk about science. I mean, even when I was working in tech, I was always that annoying person at lunch that was wanting to talk about spaceships, Incidentally, because of my sort of promotion and study, whatever, interest in asteroids, I do have an asteroid named after me. 33434, Scott Manley, originally known as 1999 FU. And that is purely a coincidence, but I kind of like it because it gets a giggle. How do you get an asteroid named after you? Well, actually, what happens is somebody gets the right to name an asteroid and then they name it for you. So you have to be the first person to see this object. You have to track it, and if you track it enough that you can figure out where it is, then you get a provisional designation. That provisional designation is when it was discovered. So 1999 was when it was discovered. F says that it was discovered in the second half of March. So they split it into 2-week sections for each letter. And the U is the number that it was discovered. And nowadays it's FU 36 because they've discovered hundreds of objects. But that's not enough. You've got just enough to know where it is, but you can still lose it. And people have definitely lost these things. You have to keep watching for years after years, typically 4 oppositions, so that you've got enough data that you're not going to lose it again. And once you've got that, you get a number, and you can name it after your favorite pop star, rock star, cat, whatever, right? And so to be clear, the object that's named after me, it was named 1999 FU, but it was originally 1989 GA6. Yeah, somebody found it, and then they lost it. But it was the actual discovery was credited to this observatory doing the 𝗖cie asteroid survey. And once the orbit of 1999 FU got really well determined, you can predict where it will be, so you can always find it again. You can also run it backwards in time, back to the 1950s, and you can find that somebody actually imaged it in 1954. This is called a pre-covery image. And it's really useful if you're trying to figure out whether an object's going to hit the Earth, because now you instantly have decades of track that let you know where it was. So anyway, yeah, that's a really kind of interest. I don't know, it's a crash course in how you name asteroids. But I'm going to say, yeah, I need to come up with a bit of humility here. Yes, I've got a planet named after me, but there's another object called 2509 Mr. Spock, which we all know is named after Mr. Spock, right? The cat. Because you can't name asteroids after fictional characters, or at least you couldn't at the time. So I'm less important than an astronomer's cat in the pecking order of things. Anyway, the way I sort of switched forward was to this game called Kerbal Space Program. It came out in 2011, and instantly I had just enough knowledge to teach people a little, and also figure out that I needed to learn a whole lot more about rocket science and orbital mechanics and things like this. It's, at this point it's stopped being developed, but it still, sits in the heart of many people that have developed spacecraft and rockets and stuff. I was at the Liquid Propulsion Symposium, and there were dozens of rocket teams building real, honest-to-God, liquid-fueled engines, and every single one of them was Kerbal was the thing that made them want to do this. So it's been a fantastic influence. But for those of you who don't know, Kerbal Space Program, you build rockets, you fly rockets, they follow the laws of physics. You can build the Apollo spacecraft. You can build space shuttles. Space shuttles are really hard because the center of mass and the thrust actually change quite a bit as it burns fuel. You can build the space station. You can actually try to launch the space station in one go if you're really weird. You have aerodynamics, so you can build planes, but hey, you can build anything really, right? You can build dragons. Dragons are cool. But if you've got really stupid ideas, if you think your ideas are stupid, you just have to look at the 1950s and 60s where everything was being suggested. Here's a rocket-powered lawn chair that was suggested for NASA. This was the idea that if you had the lunar module and it landed on the moon and something went wrong, you could just have like this kit, like a roadside assistant kit where you would basically build another spaceship and take the fuel from the lander and you could fly back to space in your spacesuit and rendezvous. One of my favorite things about this is basically, you're trying to minimize the amount of mass that's involved. So those like steering jets, they add mass, right? If we could get rid of those steering jets and the control stick, you could certainly make it lighter. So one engineer came up with something called kinesthetic steering. Kinesthetic steering essentially says if the engine is firing, you can adjust your turn rate just by leaning left and right. It's like for snowboarding or whatever. They actually built a simulator for this. They put like people in spacesuits and they were measuring their weight distribution and feeding that into a simulator. It was like a board with a bunch of potentiometers in the corner and everything. They basically invented the Wii balance board, which was, I actually hooked that up to Kerbal Space Program. And here's my son flying an aircraft badly using it. He also turned out all right. So anyway, as I said, this game has been hugely influential. 𝗖𝗀 had this joke that he worked at NASA and he only really understood orbital mechanics when he started playing this game. There's all sorts of teachers that will say great things, and then there's some guy called Elon Musk that gives it a lot of credit. Kerbal was sort of really coming to prominence just around the time when SpaceX were blowing people's minds by landing rockets. And of course, Kerbal players had to actually try to do this themselves. There were various levels of trying to land rockets. It was actually very difficult to have them land and not fall over. This was an interesting solution to stopping it fall over, right? And I honestly think that maybe there's some influence here on the 𝗖𝗀 landing technique. This is actually one that I did before we actually saw what 𝗖𝗀 looked like. So I was quite happy that this looked exactly like the real thing. I did, however, cheat by playing the video backwards. This is, of course, what a real catch looks like. This is the camera looking straight up that exhaust as the booster comes in. It is, wow. I'd love to see that in person one day. Well, maybe not from that viewpoint, but getting pretty close. This is like an insane level of control that you need to move something with this accuracy to land it on those pins. And they've made the arms smaller in the new version, right? Anyway, the great thing about Kerbal, of course, is you can simulate that. And here's somebody that's running a simulation. They're running their own code. They're running their own flight software on this simulated object. And of course, they bring this thing all the way down to a catch. And I'm not going to play it because we are kind of running all the way late. But I did want to bring something that I did sort of originally to show that I am just talking about stuff. I occasionally do interesting stuff. So this is implemented using a thing called Kerbal RPC, right? It allows you to basically connect software of your choice, C#, Python, C, whatever your thing is. Yeah, here it is here. You can download it, install it, and then start controlling your game. So you don't have to play the game, you can have your computer play the game, because that's what games are all about, right? I wanted to write a version of the flight control algorithm for the Surveyor spacecraft, which were America's first landers on the moon, and they used 4 different radar beams. They would get ranging and Doppler on them so they could figure out the attitude for deceleration and the distance to the landing and everything, and they could control this down to a soft landing on the surface. But I didn't want to use, just like the 1960s version, which was a whole bunch of, analog circuits and stuff. I wanted to use something from my past. I wanted to use a ZX Sinclair ZX Spectrum to control a spacecraft. And yeah, here's the specs. As I said, this is what it looks like. I mean, boy, look at the number of chips on that. Yeah, it's got a 3.5 megahertz processor, 48 kilobytes of RAM. It's actually comparable to what they used to land the Apollo missions on the moon, but it's kind of a little short. Anyway, The way I had to do this was I'd take Kerbal RPC, have a Python program that read it would read the state, and then it would turn that into simulated radar returns, including like noise and the Doppler shift, and then it would feed that to the spectrum via the serial interface. And then the spectrum would then do its math and send the result back via serial, which would be computed to, sent to the game. And this is it running. Now, interesting thing here is if you look at the top right, that is the spectrum doing its like descent calculations. There's like 3 numbers for like distance, speed, and computed like thrust requirements. That flickering border is when it's reading the serial port. And this spectrum was really austere in terms of its capabilities, its interfacing. It's actually bit banging those serial lines with a CPU, like manually setting values up and down. It spends almost all its CPU just reading the serial line. Actually landing computation is really, really simple. Anyway, so to follow up, there was this tweet that appeared like last week from Peter Diamandis. He started the X Prize, Spaceship One, and all that, pointing out that our iPhones are vastly more powerful than what was used to land on the moon. In fact, my iPhone is more powerful than the fastest computer in the world when I was doing my PhD work, right? The ASCII read was 1 teraflop, and modern iPhones are more than 1 teraflop of performance. My response to Peter was to say, actually, your iPhone's charger probably has more CPU power than what we used to land on the moon. And this is a table showing the microcontrollers that were found in a number of chargers. And this is actually 5 years old. So the amount of compute that has been deployed around the world has probably grown since then. But yeah, see, it had this like an ARM Cortex core running at 48 megahertz with 8 kilobytes of RAM, 128 kilobits of flash. That's enough to control a spacecraft. And we've sort of seen this through history, that computers just get faster and faster and faster. It used to be that people were impressed that we could build something the size of this room that could think faster than a human. And eventually we could put that on a truck and then into a spaceship, and then hobbyists could build it in their garage, or you could buy that at W.H. Smith's or whatever. Now you put it on a chip. And we've got to the point that, yeah, sure, my phone's more powerful, my watch is more powerful, the charger is more powerful. There are now disposable electronics which are more powerful than the computers used to land humans on the moon 50 plus years ago. And here's an example. So I've seen a bunch of you with really cool small electronics that fit inside these PocketQubes. Fantastic. So this is a device, modern, it's a low power device. It's so low cost that people literally throw these away, and you can find them by the side of roads and trash, whatever, bins. It has sensors, it has onboard processing, it has I/O. It deals with like power, thermals, fluids. It is the core of a disposable vape. Yeah, this particular one has like a screen and everything on it, but there's a guy up in Washington in the US, he's been taking these things apart that he finds and essentially building battery packs to recycle them, because we don't want to have a bunch of vapes sitting in a room with their batteries overheating. I hear that bad things happen. Yeah. Okay, I was worried this might be a difficult audience to talk about vape pens, right? Anyway, yeah, this is the hardware. You can see a close-up of the chip there. I found the data sheet for it, so it is like 48 megahertz, 8 kilobytes of memory. And I could totally build something with this. I know a guy, Tube Time, Eric Schlipfer, he has managed to pull up, specs on a lot of these things. He's reverse engineered the circuits. He's got tool chains enough to build useful stuff that runs on these. And I really had wanted to come here with a working demo, but I'm not quite that smart just yet. I'm still working on it. Nevertheless, this is an example of where I'm kind of going, and it should be fast enough if I can get it to stop crashing. So anyway, I know we're sort of running late, so I actually am going to end with one last thing that I use an even more austere flight computer probably the slowest flight computer that anyone here has to deal with, and that is this thing. It's called an 𝗖𝗁 flight computer. It's a fancy slide rule. And this is what pilots use for such a long time to do your basic math in the cockpit. You calculate your airspeed and fuel consumption and things like that. Now, the one on the left, I bought from Amazon a few years ago. It's labeled flight computer, and Amazon tried to sell me electronics insurance on it. The one on the right was a fan. He saw the one on the left, and he said, "Hey, I have something like that from my grandpa." And he sent it over to me, and I cleaned it up, got it working again. This is a 1942 𝗖𝗁 flight computer. This was the first time the US Army Air Force, this was before it was the Air Force, it was the Army Air Force, the first flight computers they issued in 1942, just as they were about to join World War II. And I used that to pass my written test in the 21st century using basically an 80-year-old computer, and I got 100% on it. So yes, the math still checks out today. I think that's a good place to leave this, unless you have one more minute? Okay, we have one more minute. Okay. There's one last really silly thing I want to drop on you guys. End of the day, let's relax a little. On the subject of asteroid names, you know this guy, Brian May. He's an astronomer, a rock guitarist. He has an asteroid named after him. Well, I thought it would be interesting to see who are the biggest rock stars out there, because as I said, you get to name an asteroid, you name it after your favorite singer, right? So I ranked these things. So on the left, you've got the number, the ranking. The second number is the number of the asteroid. Then we have the name, and then we have the magnitude. And of course, the lower the magnitude, the bigger the asteroid. So Liz Fraser, yeah, from the Cocteau Twins. She's Scottish, right? Okay, she's got the smallest one, but she's still a rock star as far as I'm concerned. We get Ariana Grande in there, of course, defying gravity and all that, right? Chuck Berry, yeah, of course, he's actually in deep space on the Voyager spacecraft, if you don't know. Moving up, we have, Bill Haley. It's hard actually to tell the difference between a comet and an asteroid sometimes. We have Shatner. Yes, William Shatner does actually release music. Once you hear it, you will never forget it. Brian May comes in at number 22. Freddie Mercury is at number 20. He's slightly bigger. Buddy Holly and Elvis, pretty close together. Also Sophie, I believe, also Scottish. Unfortunately, no longer with us. Moving up, we get the Beatles. So who's the biggest Beatle? John Lennon is smallest, then Ringo Starr, then Paul McCartney, and George Harrison, number one. Number one out of the Beatles. Who is the biggest rock star ever? Anyone want to guess? He's in there? No, he was further down. No, the biggest rock star is Led Zeppelin. I mean, that's pretty darn appropriate. So anyway, that was just a silly thing that I like to put in at the end, because people like to rank their favorite musicians and whatnot. So thanks for being an audience. You can ask me more questions later, but I know that we are well over time. And thanks for letting me come here.